And then you can transform this equation into the equation for momentum thickness. The momentum thickness is defined as basically a normalized version of this, right? So basically inside the boundary layer, how much momentum has it lost? So this is basically how much momentum has it lost. So if you have a real boundary layer versus a kind of hypothetical boundary layer that is ideal with the same mass flux. So the ideal boundary layer is basically a boundary layer that is like that and 0, right? Like a step function. The momentum thickness is basically saying that how much less momentum does the green one, the real one, has compared to the blue one, which is a step function with the same mass flux. So the mass flux is always integral from 0 to infinity of u times dy. And for the ideal boundary layer, the momentum is integration from 0 to infinity, to some kind of a ye, to the edge of ue, which is the velocity, times u dy. So this is the constant velocity ue times the mass flux. While for the real boundary layer, the momentum is, so this is ideal, this is real, is ye of u squared dy. So the momentum thickness is basically a non-dimensionalized, a velocity square scaled thickness, the difference between the momentum. So 1 over ue square times, now I can integrate to infinity, because once I take the difference is not sensitive to the precise definition of ye. So u minus u square dy. So that's the definition of the momentum thickness, right?
In the ideal case, isn't it just u squared?
It's not u squared because I can't integrate all the way to the boundary, right? It's the difference between the real boundary and an ideal boundary, not all the way up to the wall, but with some defect in order to conserve the same mass flux.
So is u a step function of 1?
Yes, for the blue case, for the ideal case, it's a step function between 1 and 0. So this is the wall, right? So it's 0 for a while and gets to be 1.
Or ue.
Oh, to be ue, yeah, that's right.
So you need the displacement thickness to get that, to calculate the momentum thickness?
That's right. So this is like the displacement thickness. Yeah, that's right. I mean, that's one way to calculate it, right? Or if you know the boundary layer profile, you can directly put that into this this equation. All right. Okay. Any other questions? No? Okay. So now, if I look at the derivative, d theta dx, what is it? Okay. It is the composition of two terms. One term is the effect of an increase or decrease of 1 over ue squared, right? That would give me minus minus 2 times ue cubed, right? due dx times the integral. Okay, the second term is 1 over ue squared times the x derivative of what we had before, the defect in the momentum. So 1 minus m times due dx plus tau. All right. And now tau over UE squared is called the skin friction coefficient. I mean, usually so tau over half of U squared is the skin friction coefficient. I think there is a density I'm missing somewhere. I think this should be tau over rho. Let me see, where did I miss it? Oh, okay, so here. Huh? Right, I think I dropped it because of incompatibility. So the real tau should be 1 over rho times that. Is that right?
Yeah.
Sorry?
You have a new there. It should be now. And then just the new dy.
Right. So tau should be defined as mu of this, right?
Yeah.
So this shouldn't be really tau, but tau over rho, right? So this should be tau over rho. And here should be tau over rho, here should be tau over rho. So all the tau should be in the equation should be replaced by tau over rho. Over rho here. Okay, so d theta dx is equal to that. And now if you look at this equation, if you look at the first term, the UE cube times this is basically minus 2 over UE times the momentum thickness itself, right? Times dUE dx. So this is one term, another term minus so m over UE is what? The displacement thickness, right? M is the mass flux defect. So minus again delta star over UE dUE dx, and then plus tau over rho UE squared is 2 times the skin friction coefficient, where skin friction coefficient is defined as tau over half of rho UE squared.